All right, here we are for this AP free response problem from 1999. Going to be honest with you, haven't worked this problem in a long time. We'll see how this goes. So I see we have this kind of interesting system here. It says, as shown above, there's this uniform disc mounted to an axle, free to rotate without friction. Thin uniform rod is attached to the disc so that it'll rotate with it. So it's like pinned here, okay, to the disc. The block is attached to the end of the rod there. Property of the disc, block, and rod are as follows. Disc to the mass, 3m, radius, r. Moment of inertia, you say, hey, look, I know for a disc it's 1/2 mr squared. 1/2 times a mass of 3m would be 1.5 mr squared. Does that make sense? The rod, you say, hey, this rod's pivoting around its end. I know the formula for a rod around its end is 1/3 the mass times the length squared. 1/3 m, and the length is 2r. So if I square that, that would be 4r squared. So 1/2 m times 4r squared. You say, what did I say? 1/3 mr squared, sorry. 1/3 m times 4r squared. You say 1/3 m 4r squared. That works out right. The block, they don't tell you the moment of inertia, but they do tell you it's got a mass 2m. What we're going to do is that we're going to go ahead, and I'm pretty confident that at the end we're going to treat that block like it's a point particle. If I got to find a moment of inertia for it, like all that mass is just focused at a point, I suspect is what we'll end up doing. All right, so here we go. I notice there's a string attached there. I bet that we'll cut that string and this will fall and rotate this is what I'm going to guess is going to happen. Okay, the system is held in equilibrium with the rod at an angle theta naught to the vertical. Okay, so angle to the vertical, shown above, by a horizontal string of negligible mass with one end attached to the disc and the other end to the wall. Express your answers in terms of m, r, theta naught, and g. Find the tension in that string. It's that tension that's holding it there. All right, so we're going to do a little, say it's in equilibrium. And so we know the sum of the forces is 0 and the sum of the torques is 0. I'm going to do a sum of the torques is 0, I think, all right, to find that tension in the string. So let's do this. Yeah. Okay, I'm going to have this like this so that I can see the diagram still, okay, and that information. So I'm going to kind of keep that like that. All right. Well, let's see here. We want to find that tension. So I'm going to do a sum of the torques is 0, right? Sum of the torques is I alpha. We're going to say it's in equilibrium, so alpha is 0. You know what I'm doing. This makes sense, all right? All right. So when I think about this setup, and I'm going to think about, what's going to exert a torque. Let me draw my sketch here. I'm probably going to be upset later that I made this diagram so small, but we'll go with it for right now. All right, I've got this rod with the block on the end that's at this angle theta naught. All right, here we go. So we say what forces are acting here, right? And you say, well, I know there's this tension going this way. That's the thing I'm going to try to solve for. I also know there's going to be like let's see, what do I want to make my system? Well, we're not including the stand here. So let's just go ahead and do disc, block, and rod as one big system. They're all attached to each other rigidly, and they're going to rotate together. So I'm going to make my system that I'm going to analyze here be, again, disc, rod, and block. So outside forces will be a gravitational force. There'll be gravitational force on the disc. The disc has a mass of 3m, so that's a 3mg. So gravitational force on the rod, again, I'm going to draw it from the center of mass of the rod, right? Now the disc we know has a radius r. The rod has a length 2r, so that's actually going to be at r out from the edge. It's actually going to be right there, where that gravitational force on the rod is. And the rod is a mass of m, so that's an mg there. Okay, at a distance, r out from the middle. It's r. All right. Now the block, there'll be a gravitational force on the block. That's acting at a distance 2r out, because that's the length of the rod. And we're treating it like a point particle. Its mass is 2m, so this is 2mg. The only other force here on the system is going to be a normal force on the axle, right? Normal force from the axle. All right. Now, if I'm doing my torques, You're saying, okay, I've got 1, 2, 3, 4, 5 forces. Right away, you can see that 2 of them are not going to exert a torque because they act at the axis of rotation. They're going to rotate around. That's the normal, or try to rotate around. That's the normal force in the axle, and that 3 mg not going to exert any torque. So I just have to worry about 3 torques. Okay, which way would you like to call positive? Now, I'm betting we're going to clip that string, and it's going to start to accelerate around this way. Why don't we make that way the positive direction? So I'm going to do torques counterclockwise minus torques clockwise. All right, is the way I'm going to set this up. So I'm going to add up all my counterclock torques. So that would be the torque from T 2mg and the torque from mg. So let's see here. I wish I had better names for these forces, but that's okay. So my torques, yeah, sure, I'll just write it like that. I have my torque from mg and my torque, and these are subscripts I'm putting on here, from the 2mg. So that's from the rod, that's from the block. And then I've got a torque from that tension going the other way, so minus the torque from the tension force. Okay, and then we want these torques to balance out. All right, we're going to calculate our torques using our formula that torque is R cross F. Oops, got to give myself some space here. I really probably shouldn't be jamming this in here. Torque is R cross F, and that cross product means we've got a sine theta in there, where theta is the angle between R and F. So running through these, the distance from the axis is what that little r is. The distance from the axis where the torque from gravity acts, that gravitational force on the rod, you say, hey, that's acting right at R. So that'll be R, and the force F is mg. And the angle there, you're like, okay, I want the angle between the R vector and the force. R vector goes from the axis, that away, okay, to the point where that force acts. I want the angle between the way the R is pointing and the way gravity is pointing. That would be this angle here. Do you see that? That's going to be theta for this guy. Incidentally, that's also going to be theta, the R for this guy, and that, right? That's going to go that way. It's going to be the same angle for this guy. These will both be at the same angle between their R and their F. Okay, I want the sine of that angle. Now, the sine of an angle is equal to the sine of its supplement. We figured that out, right? Angle adds to 180. Okay. And the question is, we have to do this in terms of the angle they gave us. They gave us this angle the rod makes with the vertical, which is theta naught. Okay, can you tell that that is going to be the same as this little angle here? This is theta naught, so this is 180 minus theta naught, but the sine of 180 of angle and a supplement are the same. So this is actually just going to be sine theta naught. All right, same thing is going to happen with this other torque. That'll be 2mg, that's at a distance 2r out. That's my r. And then the force is 2mg. And I'll have another sine theta naught. Okay. Again, because the angle that this line makes with the vertical is told us, we were told that that's theta naught. And here, right here, is a angle that this line makes with the vertical, right? So vertical, same thing. This theta, the same. Okay. And same sign for that as we have for this. All right. Supplementary angles have same sign. Okay, got it. Okay, now at minus the torque from the tension. So that'll be R. It's happening at the radius of the disk, which is big R out. The force is T. And I need to multiply that by the sine of the angle between this R vector from the axis to where the force acts, to the, you say, well, that angle, that's a 90 between that R vector and that force, right? That way and that way, that's a 90. So it'd be sine 90. Well, the sine of 90 is just 1, so that's convenient. Okay, and those should add up to 0. All right. This is looking good. We're trying to solve for t. I'm going to move this rt to the other side. Actually, you know what? First, do you see there's an r in every term? Bam, bam, bam. Sine 90 is just 1. So this is just minus t. Let's move the t to the other side. So t will be this. So t is going to be mg sine theta naught plus 2 times 2 is 4 mg sine theta naught. It's t. Let's just call that 5 mg sine theta naught. All right, and that is, yes, what they wanted us to find. Ta-da! All right. I'm sorry my diagram was so small and cramped. I probably should have just gone ahead and used the space. It made it bigger. I apologize. If you got questions on this one, make sure you ask me about those angles, but I think you're good. I hope you're good. Okay, if you got questions, I can draw it nicer for you. Okay, part B. The string is now cut, as we suspected they would, and the disc rod block system is free to rotate. Determine the following for the instant immediately after the string's cut. So before it's been able to go through any distance, it's going to have some starting acceleration here. What's the size of that angular acceleration? And then we're going to find the linear acceleration of the mass on the end. Oh, that'll be fine. Okay, so let's do that. We're trying to find the angular acceleration at the first instant. Angular acceleration, that is alpha. And we're going to find the alpha. So we do the same setup, but when we cut the string, what's going to be different? This torque will be gone now, right? That tension will be gone, and so that torque will be gone. So it's just going to be these two now. So we're going to do sum of the torques is I alpha. And we're going to have this torque from mg and this torque from the 2mg force, right? From those two. But that's it. Is I alpha. All right. These torques, we already figured out what these are. We know these are going to add up to be 5 mg sine theta, aren't they? We got that from before. So really, the tricky part of getting this alpha, we got to figure out what the I is, our moment of inertia. And you say, I know that moment of inertia is the sum of the mr squareds. So my moment of inertia, and you say, well, they actually told me the moment of inertia for these guys. For the disk going around the middle, which is what it's doing, it's I'm going to write that as 3 halves mr squared. Okay, plus, that's the disk. Now the rod, they told us, look, the I for the rod is moment around one end, which is what it's doing. It's pivoting around an end of the rod, is 4/3 mr squared. Now I got to do the block. They didn't give me the dimensions for the block, right? And it's a rectangular solid, which I don't really know like a formula for moment of inertia for. I really wish they had said something about the block being tiny or small, or its dimensions are small compared to the rod and the disc or something, so that we'd feel a little bit better about this. But honestly, I don't see any other way of calculating this other than assuming that the block is a tiny little mass, treating it like a point mass. In the sketch, it looks pretty small compared to this other stuff. So I'm going to treat it like a point particle. And the formula for I for a point particle is mr squared. So it'll be its mass, which is 2m, times its distance from the axis squared. Its distance from the axis is what's at the end of that rod, which has a length 2r. So it'll be 2r squared. I am using my formula that I is the sum of the mr squareds. Okay, is the formula I'm using there. All right, and then I still have this alpha. All right, so this is it. So I just need to, let's resolve this, move it over here, and get my alpha. Let's see here. mr squared, mr squared, mr squared, mr squared, if you're careful with that. So we have, now let's just kind of combine these terms. This is actually 2 squared, so that's a 4 times 2 is 8. So I've got 8 plus 4/3 plus 3 halves. You know, like I got to add 8 plus 4/3 plus 3 halves. Right? And there's an alpha there. And you say, all right, well, gosh, common denominator here is going to be sixths. Okay. So this will be 9/6 and 8/6 and 48/6, right? mr squared alpha. Okay. And so that'll be what? 17 plus 48 is 65, right? That sounds right. That sounds right. 65 sixths. Whew. Okay, so I'm going to move this to the other side. Well, actually, hang on a second before we do that. 5 mg sine theta naught. That's a theta naught. All right, so at that first instant before we tilted through any angle yet, we first cut the string, it's at theta naught. We can right away see that an m is going to drop, right? Bam, bam. Okay. Nothing else is going to drop here. Well, I could probably factor a 5 out. We'll do that in a second. Let's go ahead and move this to the other side by multiplying, by dividing by 65 6r squared. So that'll be 6 over 65. And I'll have that r squared in the denominator, right, when I move this over. All right. Okay. I can definitely factor a 5 out here. This is 5 times 13, so it'll be 6/13. Times g over r squared times the sine of theta naught is my alpha. All right. So that's what I got for that initial angular acceleration when we first snipped the string. All right. How do I feel about that? Well, I think I might have an error here somewhere. No. Error? Me? Never. Okay. You know what my error is? Holy cow. I bet you've been looking at this for a while. Look what I did. I put this tension in for the torque. Oh my gosh. What is my deal? What is my deal here? See that? See how I canceled that R out? We can't cancel that R out, okay? Because we're just doing the torque. Sorry. I need this line here, right? Do you see what I'm saying? I can't cancel that R out. Okay. My bad. Okay, so that R is still going to hang out in there. I apologize. So the torque here, there's an R there also. All right, so for the torque. And so there'll be another R still here and an R there, and that'll cancel with one of those R's. Bam, bam. Okay, so that's gone. Okay, there we go. That's it. Okay, so now, like, you know, my units will come out right. G is in meters per second squared, and R is in meters. So meters over meters per second squared. The meters will cancel. I'll just get 1 over second squared. That's the unit for angular acceleration. So it will work out. Okay, sorry about that. Okay, that's part B. Okay, which takes us to part C here. I'm sorry, that was BI, right? Okay, we now want to find the linear acceleration of the mass on the end of the rod. And you say, okay, that's not bad. This bit is whipping around. All of this, these are all rigidly attached to each other. The block and the rod and the disc, they're all connected. So they move together. So they all have the same alpha. They go through the same, they'd have the same omega, the same alpha, the same angular displacement, because they're all moving together. And so with that, that was part I. Part II, you say, I can find that linear acceleration, right, of the mass at the end. You say, I'm just going to use the formula that links alpha and A together. A is R alpha. Okay, and I can use this as long as we're looking at a point on this thing. Now, when I do this, the alpha we have an expression for. What's the R? That's the distance from the axis of rotation to where that guy is acting. That distance is 2r out, right? The radius of this is r. This is 2r out. So it's going to be 2r times that alpha from before. Six thirteenths G sine theta naught over R. There we go. And so, tidying this up, that's just going to be 12/13, right? This R is going to cancel that R. Hooray. So I'm going to end up with 12/13 G sine theta, right? Because this R and that R will cancel each other. And taking a look at this, you say, I know sine theta has no units. Look, A and G, they have the same units. Acceleration to gravity, meters per second squared, meters per second squared. Life is good. Okay, so that's our answer for part BII. Okay, B2. All right. On to the next part. So now it says, now this is rotate, 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 speeding up faster, faster, faster. As the disk rotates, the rod passes through horizontal. At that point, find the linear speed of the mass at the end of the rod for the instant it's in the horizontal position. All right. All right. I see what's going to happen here. All right. So, grabbing myself another piece of paper. So, you know how we calculated in the previous part, we calculated an angular acceleration, right, in BI, right? So you might say, well, can I go ahead then, and we're trying to find a linear speed here. So maybe I can find my angular velocity here, my omega, and then do V as R omega and find that, right? Can I do that? In other words, can I use those kinematics equations? Do I have, and you say, well, what's the limitation on using kinematics equations? You say, those all require a constant acceleration. And the rotational version requires a constant alpha, a constant angular acceleration, which requires, just like a constant A requires a constant force, a constant alpha requires a constant torque. So we got to back up here and say, hey, that acceleration we calculated here, that alpha, is it the same for that whole turn? And you say, well, that's not going to be the case. These forces will stay the same while we're rotating. It's still mg. It's still 2mg pulling down. But that angle that force makes with the r vector is going to be changing. And so if that angle changes, my r cross f, that depends on the sign of the angle, is going to be changing. So my torque changes, so my alpha changes. So I cannot use the rotational kinematics formulas for this last part, which is too bad. Okay, so you say, so what do I do typically when I have a problem and I need to find some velocities or whatever, and my acceleration is changing as I go? If I had an equation for acceleration as a function of time or something, I could do something tricky with integrating to find my delta V, right? Finding my area under the alpha, the AR graph to find the delta V. But I don't have an equation for alpha as a function of time. So instead, you remember what we do with force problems? I got something that's moving from point A to point B, but the force is changing as I move along. What we usually do is we use energy, and we just use potential energy going into kinetic. And then you don't care about the path you take, just the starting and the final configuration, the arrangement determines the potential energy change, and that energy goes into kinetic, and life is good. That's what we're going to do here. In this case, you know that what's driving this thing is gravitational force. And so if I include the Earth in the system, I'm going to be rearranging the position here. And my center of mass of the system is going to be dropping, isn't it? As this thing falls. And so I'm losing gravitational potential energy, turning it into rotational kinetic, because we're not translating anywhere, we're just spinning. So that's going to be, I think, the best approach to do here. All right. So I'm going to get myself some fresh paper, and we're going to figure this out. All right. So first of all, we are doing part C. Okay. And we're going to do our system is going to be disk, block, and rod. Okay, because they're all rotating together like one big object. I'm going to treat that as my system, but I'm also going to include the Earth so that I can have a gravitational potential energy, so that then I don't have, so the gravitational force is now not a force from outside the system, so I don't care that the work it's doing is going to be tricky to, I don't care that the angle's changing with it or anything. I can just treat it as part of the system, so now it's a force inside, that gravitational force, so it's not going to be an outside force doing work, right? And I don't have to try to calculate the work through that weird path. So here we go. Sigma W is delta K is the way we would start, but because I'm including the Earth, I can also have a delta UG. Now, what kind of kinetic are we talking about here? We're not translating anywhere. We're just rotating. We're pivoting, right? So this will be my rotational kinetic energy. What outside forces are doing work here? You say, well, look, take a look at my diagram now. This was for a combined system of disk, rod, block. The only outside forces were this tension, which is now gone because that string is clipped. There's a normal force from the axle, and there's these three gravitational. Now, the gravitationals go away because the Earth is part of our system. We're going to have potential energy changes instead of those doing work. So I really just have the normal force from the axle. Will that do work? And you see, now in order to do work, it has to push through a distance. This is just spinning around where that force acts. That force isn't pushing through a distance, and so it's not doing any work. So I have no work. All right. This force is gone. This force doesn't push through a distance, and these are interactions with the Earth. They're interactions inside our system. So we're just going to have delta UGs instead. Okay, so delta K rotational, that's going to be my K rotational final minus my K rotational initial plus UG final minus UG initial, right? Now, are some of these terms going to be zero? You say, well, let's go ahead and say that I've been avoiding drawing on the original sketch. I don't know why. Why don't I draw here? Just to make this clear. We're looking as we go from this setup to this setup, right? So let's do, you say at the start here, it's starting from rest. So our starting rotational kinetic energy is 0. Why? Because we're starting from rest, our omega naught is 0, right? And K rotation is 1/2 I omega naught, or 1/2 I omega squared, I should say. So this, I'm just going to have 1/2 I omega final squared. All right, that's 0. UG now. With gravitational potential energy, you got to choose a height to call 0. Where might be convenient to call 0? Well, because I kind of am going to have to figure out, I'm given masses for these parts separate. I'm going to have to look at each part as each part drops. It might make my life easier if I call right here, isn't the center of the block and the center of the rod and the center of the disc all at the same height? So let's call this final height 0. So if I call here height 0, then here this is going to be 0 because the final height is 0 for everything. Okay. Now I'm going to have some potential energy at the start. The disk starting height is the same as its ending height. The center of the disk stays at the same height. But the rod's center of mass is going to drop from here to here, right? And the block center mass is going to drop from here to here. If I draw, so now what I'm going to do, I'm going to draw in the initial position of that rod, okay? And I hope this is going to make this simpler for us rather than more complex. But there's that rod and that thing. And we know this angle is theta naught. And we're going all the way here from theta naught to theta is 90. You know what I mean? The question is, what's the height change? Well, we know what I'm going to do is this point is the one we're interested in. I'm going to construct a little triangle here. Maybe. This is the height change. I know that, let's draw this across here. This is theta. This length is r, the radius of the disk. So this bit here is the height change, and that is going to be r cosine theta. It's the r is the hypotenuse of this right triangle. There's a right angle here. This is the height here. This is the adjacent to theta naught. So this is r sine theta naught. That's my height change. So I'm going down, right? The mass of the rod, I'm doing MGH, right? So it's going to be a minus mass of the rod, G, the height change of the rod. You know what I mean? The initial height of the rod, right? And I'm going to have a minus mass of the block, G, original height of the block. You know what I'm saying? Okay, so we just figured out that for the rod, that's going to be the mass of the rod is actually M. So that's good. G, and its original height we just figured out was r sine theta naught. What about the block? Minus the mass of the block is 2m, so that'll be 2m G. What's the starting height of the block? Well, I'm going to do the same trick there, right? I'm going to make a little triangle, or a little diagram here. It's here, and it ends up there. The height change here, if I draw over, this is the same theta naught. Now, this whole length here, that's the adjacent to the theta, and 2r is this is the hypotenuse here on this right triangle, right? It's orange right triangle, right? So this is going to be 2r sine theta naught. That's the height change for the block. So this will be a 2r sine theta naught. And we're going down that. Okay, there we go. Shoo! Okay, hey, what's left to do here? We're trying to find, once again, the linear speed of the mass at the end. I'm going to find the omega, and from the omega, I'm going to change that to find the linear speed in a minute. Okay, now to do this calculation, I need to find the I for this whole thing. Did we find that before? Did we find a moment of inertia for the whole thing? We did. We found the moment of inertia for this whole mess rotating was 65/6 mr squared. Okay, we found that before. So I'm going to put that in there. 65/6 mr squared. For my I, omega final squared. Let's move these two minus terms to the other side of the equation. So I'm going to move these two to the other side. So I've got mgr sine theta minus 4, see 2 times 2, 4 mgr sine theta. That's going to be a minus 5 mgr sine theta. Move to the other side, 5 mgr sine theta. Sine theta naught, this is actually, right? Sine theta naught. Okay. Let's see. Hey, it looks like we can cancel one of these r's. Looks like we can cancel the m. This 5, if I take a 5 out, that'll turn into 13. Right? All right. Let's stop there and let's tidy this up. This is 13/12. So that sounds familiar. 13/12 r. Yeah. Here. Okay. And over here, we've got bam, bam, bam. Gosh, what's left? Just g sine theta. Not. So clearing this over here, I'll have 12/13 g over r sine theta naught is omega final squared. We are getting close. All right. You know that this is in meters per second squared, and I'm going to divide by distance, which is in meters. That radius to be in meters. So it'll just be per second squared. Omega is radians per second. And see, I'm squaring it. So per second squared, this is working out. Okay, it's working out. So my omega final is the root of this. Okay. But we don't want omega, the angular velocity. We want the linear speed of that mass. So I'm going to do that with v is r omega. In this case, we're talking about this block out here, right? What's the r for the block? It's 2 times the radius of the disk, 2 times big R. So it's 2 times big R times this omega times the root of 12/13 G over R sine theta. Now, if you see there's an R outside the radical and R inside the radical, they'll want us, its best form is to combine those, right? I can bring the R inside, it becomes an R squared, and then it'll cancel. One of those R's gets canceled by the R on the bottom. The 2, I guess this is 4 times 3. I could pull another 2 out if I wanted to. Do you think they'll want us to do that? Sure, why not? I'm bringing the 4 out and I'm putting the R in. Whatever. So this will end up being, I pulled the 2 out. It was a 4 inside under the radical. So this would be 3/13. This will become an R squared when I put it in, and then I'll cancel with one of the R's at the bottom. So GR sine theta is my V. One last double check. Does this make logical sense? Units wise, you say this would be in meters over seconds. This is meters over second squared times meters. So that'd be meters squared over second squared. Taking the root, meters per second, meters per second. Okay, that seems legit. Okay, and that's my answer. There we go. Hot diggity. Okay, I think we're good. All right, that's that problem. Is that good? Or did I screw something up? Nope, I think that's good. I think we're all good. Yes, we are all fantastic. Okay, yep, that's it. Nope, that's not it. Ah, holy cow. All right. Okay, this is why you make nice diagrams. Hey, look at what I've been doing here. You've probably been screaming at me for the last 10 minutes. That height change. See how this is the side that's adjacent to theta? It's not sine theta, it'd be cosine. Duh. Sorry about that. That's a cosine theta naught. And same thing for this one. Those are cosines, not sines. I'm sorry. So when I get into here, this is cosine. And that's cosine. I know, you're like, that's not very clear, Mr. C. Sorry. Okay, when I combine them, minus mgr cosine theta and minus 4 mgr cosine theta, that'll be a minus 5 mgr cosine theta. Tracking all the way through. That's a cosine. Dang it. That's a cosine. And that's a cosine. And that's a cosine in our final answer. Sorry about that. So there. Okay, that's what we get. Yep. Okay. Okay, that's it. That's the problem.